if you've ever done a geometry course or a few problems, you know that the volume of a cone is equal to 1/3 pi r² multiplied by h, which is the height. In this video, we're going to go over how to derive the volume of a cone using calculus. And to do that, we're going to go over what a cone is and what it's composed of. So a cone is composed of a bunch of tiny cylinders. Okay, so that might be a little hard to imagine because you're going like, wait, a cylinder, it has a straight height, and over here you can see that the sides of a cone are kind of slanted, right? So how does that work? So you might have heard that a cone is a bunch of circles stacked up on each other which have radius or radii that are getting smaller. That's actually not completely true because a circle is a 2D shape, right? So if you keep stacking it on each other, the height isn't going to go anywhere. You're just putting a bunch of circles on top of each other. There's really no difference. But what you really are doing is you're putting a bunch of cylinders on each other that are super duper thin. So this height of the cylinder right here is the closest number to 0, right? So that's its height, and that's why you see a difference in height every single time a new circle with a smaller radius is added on top. Okay, so in this video, we're going to use calculus to find the integral of the area with respect to the heights that are really, really tiny, to find the sum of all those tiny cylinders and get the total volume of a cone. Okay, so let's start with that. And as I said before, the volume is equal to the integral of the area of all these tiny cylinders with respect to the height of each cylinder. Like I said before, the height of each cylinder is so tiny that it's the closest number to 0, and that's why we're integrating with respect to h. And over here, you might be like, okay, so what are our limits? So because at the base of our cone, the height is equal to 0, we're going to start with 0 over here, and we're going to end with the highest point, h. So as I defined in this figure over here, the highest, from the bottom to the highest point, the height of the cone is h, and the radius at the bottom of the cone is uppercase R, so uppercase H and uppercase R. It's going to get a little confusing with all the variables, so it's important to remember that. Okay, so over here at the top of our limit, we're going to write uppercase H. Okay, now we have to substitute something for a, so we need to substitute the area so that we can start integrating. Over here, like I said before, the height of each cylinder is the closest number to 0, so that means that we can treat each of those cylinders as a circle, almost. That's why that's why there's that general confusion between the circles being stacked on top of each other rather than the cylinders. So over here, what we're going to say is V is equal to the integral of pi tiny r squared dh from 0 to uppercase h. Okay. So now you might be wondering, wait, we need our equation in terms of uppercase R and uppercase H, right? Because that's how we wrote it. That's the equation that that's the equation that we're supposed to get at the end. But over here we have lowercase r and lowercase h, and we really can't do anything with that. So that's why we're gonna go look at this figure over here. Over here, I defined, as I said before, I defined the total height of the cone as uppercase H and the radius of the base as uppercase R. So what we're going to do is we're going to take the small cylinder right here in the middle, right? So it's somewhere in the middle, but we're going to take our reference point as right here, and we're going to draw a tiny radius because, as I said before, the radius is getting smaller and smaller throughout the cone. So we're going to define this as lowercase r, and we're going to define the height of this tiny cone, so going from this point to the top again, as lowercase h. Okay, so now after I drew all of that, you might have seen that there are two triangles formed. You have this big one over here with uppercase H, the total height, and uppercase R, the radius at the bottom, and obviously the radius in the middle, and the height from this point to the top. So these are similar triangles because the radii are always parallel to each other, right? So that means all the angles over here are congruent to each other, and by the AA Similarity Theorem rather, we know that these triangles are similar. And because they're similar, we can use proportions. We can say R let's use a different color. So let's say R by H, so lowercase h, is equal to uppercase R divided by uppercase h. And that makes sense, right? And like I said before, we're trying to get all of our variables in terms of uppercase R and uppercase h, and we also do want lowercase h so that we can integrate over here properly. So let's say R is equal to uppercase R lowercase h divided by uppercase h. And now that we know that, we can substitute over here. We can say volume is equal to integral of, so let's write our limit, pi, and then we can write in our brackets R h divided by uppercase h whole square dh, and now we can simplify that. So let's go down, and then we can say v is equal to integral of 0 h pi r square h square divided by h square, and then with respect to h, so dh. Okay, so now what we have to do is take out all of our constants, and we know that pi is a constant, right? It's always been. And then r squared is also constant because it's the set value of the radius of the cone at the base, right? So that's a constant, and then uppercase h is also a set value because it's the total height of the cone. Okay, so we can take all three of these out. We can say v is equal to pi r square divided by uppercase h square. So just a quick FYI, make sure that you know the difference between the uppercase variables and the lowercase. It'll help you so that you understand the whole derivation that's happening. And then you have that, so you wrote your limit, and then h square dh. Okay, and now we can just integrate that to get v is equal to pi r square divided by h square, and then we have this. So after integrating that, you get h cubed over 3, and then our limit. So we have 0 to h. And now what we have to do is, because we have that limit, we have to substitute for our final and initial values to get our answer that we want. So now we can just say v is equal to pi r square divided by uppercase h square, and now in our brackets, so this is our final value and this is our initial value, so we're going to do final minus initial, and we're going to substitute uppercase h for lowercase h. So we're going to say uppercase h cubed divided by 3 minus 0 to the power of 3 divided by 3, and we know this is equal to pi, so this is canceled out, right? So that's just 0. So pi r square divided by h square multiplied by h cubed by 3. Okay, so now we can use some of our exponent rules, and we know that if you're dividing a few exponents with the same base, so because h to the power of 3, and in the bottom you have h to the power of 2, you get h, so all you do is h to the power of 3, or no, let's write it over here. So all you have to do is h to the power of 3 minus divided by h to the power of 2 is equal to h to the power of 3 minus 2, right? So if you remember that, then you just get h. So over here, you can just say simply, these two cancel out, sort of. So over here, you just have h left. Okay, so just in case that was a little complicated, go back and review this. You can say pi r square multiplied by h divided by 3, and that's basically our original formula for the volume of a cube, which is v equals to 1 over 3 pi r square multiplied by h. And this is how you derive the volume of a cone using calculus. Thank you for watching, and I hope this helped you.